All right, welcome back, everyone. And today we're going to get into chapter two, and it's the ordered universe. And I think this is actually a really interesting chapter. We're not really going to be talking about hard science here. I'm going to be almost giving you a history lesson, but it's pretty interesting. And so let's get started. Take a look at this figure. Now, I'd venture to guess that many of us live in or around section 9 through 5, right? A place where the light pollution is extremely heavy, and it's probably difficult for us to make out many stars, if any, and certainly not other celestial bodies. Now, for those of us who might happen to live in a rural area, this isn't the case, and we're extremely fortunate, in my opinion, to be able to look up at the beauty of the night sky. The lights in the night sky are among the most predictable things in our universe. Before the 19th century development of lights, human beings only ever experienced pitch black nights with bright celestial bodies shining down. Living that way led our ancestors to discover that there were regularities in the arrangement and movement of the stars and the planets, and they're able to craft stories, put them into their religions and their mythologies that back up why certain objects move a certain way. They're able to predict when to plant crops because of where the sun would rise in the sky, and know when the moon would be full so that they could extend hunting and harvesting times by the night light of the moon. So, really, is it any surprise that astronomy, which is the study of objects in the sky, would be the first science to be developed? I don't think so. The night sky is really, really important to our ancestors, and only because of, well, increasing technologies have we sort of maybe moved on from it in a way. There's really no other symbol of humankind's early preoccupation with astronomy than this image right here. This is Stonehenge. Stonehenge is this great prehistoric stone monument on Salisbury Plain in southern England. Incredibly, Stonehenge was built by several different groups of people who most likely didn't have a written language. Some of them didn't even have metal tools. So it's this marvel of architectural achievement that is really almost beyond compare. Stonehenge was built as a tool to mark the passage of time based on the movement of celestial bodies. The most famous of its abilities was to mark the passage of the seasons. In the midsummer, if you stand directly in the middle of this monument, the sun will rise directly over one of the stones, which is known as the heel stone. Without a written language about the movement of celestial bodies, that information had to be passed down from generation to generation to make Stonehenge so incredibly accurate. But basically, what that shows just how predictable these movements are. So it's really, really incredible to think that people without a written language could predict based on what was going on in the night sky and build something this incredible. Now let's switch gears and talk about the discovery of the spread of disease. And now you might be thinking, well, this is incredibly different than what we just talked about, and you're right. But I'll show you how it ties in. During the 19th century, Europe was going through basically a pandemic. It, for certain, an outbreak of a disease called cholera. Cholera is a bacteria that causes severe, if not fatal, stomach issues. The discovery of germ theory, which basically means it's germs or it's bacteria that cause disease, was still decades away, 60, 70 years away from where we are right now. This guy, John Snow, yeah, I know that's kind of ironic. He was a London physician and a pioneer of anesthesiology. I'd like to point out that during this time, before anesthesiology, things like childbirth, things like any large amputations or surgeries were all done without anesthesiologists present. So we can thank this man for starting to figure that out. Although what he used was basically just chloroform, but I would take that over being awake during my amputation any day of the week. But anyway, he was a London physician and a very, very good scholar. At the time in London, people were getting their water to bring to their houses for all sorts of their needs from public pumps. And the water that even might have come through to, if you were a very affluent family, if you had water running into your house, it came through this maze of pumps where it was really, really hard to know the source. So in 1854, Snow discovers that the cholera outbreak seems to be centered around this Golden Square pump. It's the community of Golden Square, a very poor place. It's a poor community where they would take their human waste and basically just dump it in the backyard. And so what he argues is that this probably is contaminating the water in some way. Now, keep in mind, he had no idea about bacteria. But I mean, you do know that you don't want waste near what you eat or what you ingest into your body or put on your body. So he leads this effort that London does to say that, well, all waste is required to be dumped into sewers far away from your dwellings and certainly not upstream of any water in which the city is taking the water from. And so it's really, really incredible because what this shows is that if you take a lot of data and you use that data to support an argument, that argument can be successful in stopping something as terrible as the spread of disease. Let's take a look at this. For many, many, many years, people thought it was pretty much impossible that Stonehenge was made by anything other than, dare I say, ancient astronauts. Okay? What does that mean? Aliens. So there's no way that people had the ability, the tools to move these stones. But really, why should we immediately jump to something like, well, it must have been aliens, when we know that the resolve of human beings is so great? And with just a little bit of thinking and a little bit of understanding, we can see that, well, it actually was probably possible that these people did it. Now, not saying that it wasn't an extraordinary feat, it certainly was, but all the materials that Stonehenge is built out of, like these stones, are not stones that were found miles and miles and miles away. No, they were local. They could have been taken from the immediate area. And so if you do a little bit of math, you find that each stone weighs about 50,000 kilograms, and if you're an American, 100,000 pounds. It's incredibly large, right? But how much could somebody move? Well, a person can carry around 100 kilograms very, very easily. And it was probably snowing when these were built. And so they were probably placed on sleds. Sleds were built back then. Sleds were used. And so if you start to think about it, if you had about 500 people per stone, that's only about 100 kilograms per person. Now, am I saying that somehow organizing 500 people to do the same job back then would have been an easy feat? I'm not saying that. But what I am saying is that perhaps we shouldn't jump to, well, it must have been some sort of unknown, unforeseen, higher being that's never been proven to exist, when we are, as humans, very, very good at solving problems on our own. So that's just one little piece of evidence to say that humans, very, very genuine in their fact that they are going to do and fix problems based on their own abilities. Let's talk about the birth of modern astronomy, how astronomy came to be. So, Claudius Ptolemy, that P is silent, it's Ptolemy, is an Egyptian-born Greek astronomer and geographer. And what Ptolemy does is he proposes the first widely accepted explanation for movements of celestial bodies. In the Ptolemaic description, Earth sits unmoved, so it's not moving at all, at the center of the universe, and the stars and the planets move around it. He predicts many things that are actually going to turn out to be true. This is in the 2nd century AD. He predicts planetary motions. He predicts eclipses, other heavenly phenomena. Once again, Earth is at the center. It's not moving. Stars and planets are revolving around Earth. And this remains as the best explanation of the universe for, get this, almost 1,500 years. Nothing in science really lasts that long, right? The way science advances, we're always coming up with little tweaks and little advancements all the time. For something like this to last for that long, it was a pretty dang good explanation. Now, here's a graph of what Ptolemy suggests, the Ptolemaic system. Notice Earth here is in the very middle, of course, because why not? Because Earth was very, very important. There's other things that we'll get into about why Earth would be in the middle for these men. But think about what they're using back then. They didn't have telescopes yet. They didn't have any real scientific tools that would come about in later years. And so they're coming up with explanations based on what they see with mostly the naked eye. And so something like this, where you see smaller circles within their larger orbit, this explains why the movement of these planets is uneven in the sky. And guess what? That's correct. Pretty much almost correct. These things are rotating. So this stands, like I said, for about 1,500 years. However, during the early 16th century, so 1,500 years later, a Polish cleric by the name of Nicholas Copernicus comes about. And Copernicus, he publishes his work called On the Revolutions of the Heavenly Spheres, and he makes one major adjustment. Copernicus says, well, this is all very good and well, but actually the center of our universe is our sun. So this is a huge change, because suddenly the Earth is not at the center of the universe. And you know how they say, well, you're not the center of the universe? Well, that's going to be real troublesome for the church. Saying the Earth is no longer the center of the universe is basically next to heresy. Now, he retains things. He retains the notions of the spherical universe. And we have no explanation for why he thought this, why he devoted his life to proving it, but he does. And guess what? He was right. Here is the historical background of the Copernican system. So look, it's pretty much identical, but all of a sudden, now we've got the sun in the middle of the universe here. So really interesting. I shouldn't say the middle of the universe. I should say the middle of this galaxy. But let's move on. So we've got two hypotheses. Copernicus basically produces a hypothesis that says Earths, and in the same vein, humans aren't as special. Now, that's not what he was trying to get at, but it's how people took it. So now, astronomers are faced with proving which hypothesis is correct. I say hypothesis being correct. Really what I mean is supported, okay? But in this instance, we'll go with correct, because one actually pretty much was. The problem was the differences between the two hypotheses were so small, they couldn't really be determined using the equipment of the time. Some of the things that would have been different were at what time a full moon comes up, at what time the sun rises, and there were very minute differences that you couldn't really change with the naked eye. Until we get to the Danish nobleman Tycho Brahe that shows us the way out. By the way, Tycho was a weird guy. He had to wear a fake nose for almost his whole life because he got into a fight at school with another man over who was the better mathematician, and his nose got broken and he had to wear a prosthesis that was metal for his whole life. I just think it's interesting that he was that devoted to mathematics that he would fight over it. So here are some observations. We have Tycho, the Danish nobleman. He lives 1546 to 1601. He becomes an instant star in the scientific world because he observes a new star. What he actually sees is a supernova. He wouldn't know that at this point, but a supernova is basically the last hurrah of a dying star, where it basically explodes and becomes extremely bright, and that's what he saw. But what this is he shows that the sky actually changes. So instead of it being 100% the way that it always was, well, it actually can change. And the bigger thing that he does here is he designs and uses new instruments. One example is the quadrant. The quadrant basically takes a measurement, two measurements. One is the degrees away from north of a celestial body and the degrees above the ground of a celestial body. And he was able to not only make accurate measurements, but also account for changes in his measurements. His items were made out of brass, and he knew that brass would shrink in colder weather. And so he was able to adjust for those changes. He collected years and years, decades of data on planetary movement, all that were extremely accurate. And before he dies, he hires on Kepler, who becomes his colleague for 2 years. And Kepler takes the data after Tycho dies, and Kepler is able to produce laws. Now, the first and most important law is that planets actually have elliptical orbits. So beforehand, they've been perfectly circular orbits, but he is able to take all of this data and produce a law that says planets actually have elliptical orbits. Okay, an elliptical orbit, sorry, not an ellipsis. An elliptical is a circle that's kind of stretched out. Okay, so it's not a perfect circle, but it's kind of stretched out long ways. Take a look at what an ellipsis looks like if you want. But let's just think, in just 60 years, we have Kepler's laws. Why? Something that is 100% true to this day. For instance, that's why it's called a law. Why? Why did we take 1,500 years with something that was incorrect, and now in 60 years we have something that's correct to this day? Why is that? Give you a second to think about that. Well, the reason is because we have this new instruments. We have new instruments, we have good data, and now we have really good mathematicians who are coming up with ways to explain what that data means. And so that's why. So I'll leave you with a few questions to answer here. What two things allowed Kepler, using Tycho's data, to break through centuries of mistaken interpretation of the solar system and discover the modern concept of how our solar system and the universe works? Well, I just said the two things are extremely good data and new technology, new instruments to use. Those two things are going to propel science to this day. That's how we make new discoveries, new technology, new information leading to new explanations. That's how science works. And then the second is, what are the philosophical and religious implications of the Copernican theory of the universe compared to the Ptolemaic theory of the universe? Well, I think I said this before as well too. The church was very, very upset when they realized that the evidence was showing that Earth was not the center of the universe. If you remember when I talked about Galileo, well, Galileo came out with his own explanation, and he said the sun is the center of our universe, and he was actually put on trial for heresy. And so, unfortunately, that is the case. He was actually able to get himself off from being put in jail or put to death, I guess, at that time by claiming that he didn't actually believe what he meant. However, he was an old man at that time, and he would spend the rest of his life, which was only about 2 years, in house arrest. And interestingly enough, the Pope in the 90s came out and they totally exonerated Galileo. So there was a good ending to that story. But that's why implications of science had a real effect on the world at that time, because the number one purveyor of knowledge before that was the church. Okay, and so with that, I'm going to leave you, and I'll see you in the next lecture, which will be on chapter 16.